Hello, I'm Michael, and in today's talk, I'll show you how BIER can help to solve your problems. So at least your distance metric learning problems. So what is distance metric learning? The task of distance metric learning is to embed an image into a high-dimensional feature space. And in this space, similar images should be close to each other, and dissimilar images should be far apart from each other. And this has really many applications in computer vision, such as image retrieval, face verification, object tracking, or person reweighted. So in this talk, we're going to focus ourselves on image retrieval and what's the problem here. So what we found is that especially large embeddings tend to overfit in this area, and you can measure this, and this manifests itself in high correlation in embeddings. And that means basically that your embeddings are kind of redundant, especially if they're large. And what we're going to do to fix this? Our idea is, well, if you cannot use large embeddings, let's divide these large embeddings into smaller embeddings. So what we do is we divide the last layer of our CNN into several smaller learners, several smaller embeddings. And the question now is, since they all share a same feature representation and ImageNet CNN, how can we make this different from each other? Because if you train this on the same data set, they will all end up learning more or less the same thing. And we employed for this two tricks. So we used a special initialization method. We initialize them independently from each other. And the second thing is we use online gradient boosting. So about the initialization. So what you see here basically is the first term of this objective here in red tries to make the activations of your embedding across this of pairwise groups kind of independent from each other. The problem with just this first term is, however, that if you optimize this, you can easily achieve zero loss if you set W to 0. And that's bad because, any initialization with a zero matrix probably won't give any good results. So we add the second regularization term here, which forces the incoming row vectors of W to have about a unit norm. And we optimize this with fixed CNN features with respect to W, and that's our initialization. The second trick we employ is we train our network with online gradient boosting. So how does this work? So we basically fetch a training patch and make a forward propagation through our CNN features until our embedding ensemble. And then we look here at the loss of the first learner. So the first learner kind of computes a loss function with its embedding on the training patch. And what then happens is we look at the gradient of this loss function. And the gradient of the loss function is going to be big for quote-unquote hard samples and easy for quote-unquote low for quote-unquote easier examples. So in this case, the yellow example is kind of a hard example. That's why it's upweighted. And the next learner is trained on the same loss function, but with this reweighted data set. So it has to focus on different training examples in this mini batch. And since successive learners kind of focus on harder examples, we also allocate more neurons to them, since they have to solve harder optimization tasks, presumably. We do this for all our learners, and then for the backward pass, we just backpropagate the gradients basically to the embedding and sum it, and then backpropagate it through the CNN ImageNet features. So our method doesn't really impose any or much computational overhead, so it integrates pretty nicely into this backpropagation training of neural networks. So for evaluation, we used several data sets. So the first three are kind of the most important ones in this area. This is CUB BIRD's dataset, so a dataset with fine-grained bird classification, a CARS dataset, Stanford Online Products, and then we also evaluated on in-shop Clothes Retrieval and VehicleID. And the way this evaluation works is you split basically the labels of these data sets into groups, into a training and a testing group, and you just train your embedding on these training labels, and then at test time you should basically retrieve from your test label set instances. The evaluation metric which we employ here is recall at k. That means for a given query image, we look at the k nearest images from the database, and if one of these k images has the same label as the query image, it's considered a match and okay, and if not, it's a mismatch. So yeah, what did we try out? So we first evaluated our method on this CUP dataset and compared it to a baseline. So a baseline with an embedding of a size 512 achieves an accuracy of about 51.76%. What we then tried out is to split this large embedding into groups, into several learners, and initialize each of these with our, initialize the embedding basically with our initialization method. And we already see a quite considerable boost in accuracy, since this the small embedding sizes tend to less overfit, and since we employ this initialization method, they are kind of initialized independent from each other. If we further add boosting to this, we also see a large increase in accuracy, and what we also can observe is in the last column that the correlation kind of goes down compared to this previous initialization method. That means that through this boosting-based mechanism, our learners get more diverse to each other, and hence the accuracy can improve. Yeah, so we also looked at the number of learners in our ensemble. So for a fixed embedding size of 512, we tried 2 groups, 3 groups, 4 groups, and 5 groups, as you see here. And we looked at the correlation between each of these groups, the average accuracy of one of these learners in these groups, which is the second column here, and the last column is basically the average the ensemble accuracy on the data set. And what we really want to do is, what we really want to have is large ensemble accuracy. But our method kind of has a trade-off. So the more groups you have, the more learners you have, the more diverse these learners can get to each other. So that's shown in this first column with classifier correlation. But the problem is that especially small learners tend to underfit the data. So especially like this last learner, which has just an embedding size of 36, doesn't achieve a very high accuracy. Hence, this average accuracy of learners in an ensemble drops. And this is kind of the trade-off of our method. So our method kind of works best for this data set for an embedding size of 512 with 3 to 4 learners, as you see in this table. What we then did is we measured the effect of initialization. So we compared our initialization to random initialization, orthogonal initialization, and ours. And we see that by using our initialization method, we achieve a quite large boost over random initialization. We compare our method to the state of the art on these 3 very competitive data sets, and we see that we can improve over them by a significant margin over very recent, very good work, even here at the conference. And we also compared on fashion, also in-clothes shop retrieval and VehicleID, and we also managed to outperform very specialized methods on these data sets from last year. Qualitative results, yeah, here you see basically how these data sets look like. So this task is kind of challenging sometimes even for humans. And here is, for instance, a failure case where a car is misretrieved because it has horizontal stickers as opposed to vertical ones. Yeah. So thanks for your attention, and I hope you all enjoyed BIER. Yeah.
Questions?
I have a question to start. Oh, you have one here. Go ahead.
Hi.
I was going to ask if what type of loss if you're using. Are you just using normal kind of triplet loss?
Right.
If it was affected by the
So
different ensemble?
Thanks for the questions. It's very good questions. I didn't really talk about the loss function we're using. We evaluated this with contrastive loss, triplet loss, and what people call binomial deviance, so which is basically a weighted log loss. And our method tends to work best with this binomial deviance loss because it has kind of smooth gradients as opposed to the triplet loss and the contrastive loss. And if you look at boosting, at online gradient boosting, typically these methods kind of tend to perform a little bit better with these loss functions which have smooth weights. So I think that's the reason why it works best with this.
Thank you.
Hi, great talk. I had one more question. This idea is not necessarily restricted to embedding or metric learning, right? You might as well also try this kind of boosting idea for classification or something like that. Have you considered that?
Right, so we had in our supplemental material a slight modification of this method evaluated on Cypher 10 and compared to Dropout, because Dropout is also kind of an ensemble strategy, or has at least the interpretation of being an exponential average of different networks with a shared feature representation. And we showed that at least with small networks on Cypher 10 we can outperform Dropout. So it's, I think it's applicable to tasks beyond metric learning.
Thanks.
You have a group of a few different embeddings where the first embedding is a bit weak, the second is more stronger, and they're independent of each other. Now, since you're doing a retrieval, there's a bottleneck of computing nearest neighbors. So can this method be run in a cascade? So first take the first group of weak learners and refine from
Right.
the set that they return?
So we didn't try that. I think it's a quite interesting idea to use this really in a cascade, because it kind of really looks like this Haar cascades in object detection, where the first one is kind of very small and the second one is larger. Didn't really try that. I think the point is, you know, the most computational overhead is really going to be this forward propagation of things through the network, maybe. So that's a reason why we didn't really try it. But I think it might be for really large databases a very interesting thing to try. So if the distance computation between your elements is kind of the main computational overhead, this might really help to speed it up. But yeah, we didn't really try.
Thanks.
All right, let's thank the speaker again.